We know how to add a value. Now let's do the opposite. Let's remove a value from the middle of an array and close the gap it leaves behind. When we delete the value at index I, it leaves a gap. We do four things. We remove the value at I, we shift the later values one slot left. We drop the size by 1, and we copy front to back to close the gap. This is our array, and we will delete index 2. Look at the blue cells first. These are indices 0 and 1, the values 17 and 42. They sit before the deleted spot. They never move. Now the red cell. This is index 2, the value 8. This is the one we remove. It leaves a hole we must close. Now the amber cells with the arrow. These are the later values, 99 and 5. Each one slides one slot to the left. That fills the hole, and the old last slot is left behind. Notice how the position decides the cost. Deleting near the front shifts almost the whole array. Deleting the last element moves nothing at all. Let us watch a delete step by step. The array holds 17, 42, 8, 99, 5. The size is 5. We want to remove the 8 at index 2. Each new row shows the whole array after one copy. First copy, the counter J is 2. We copy of 3, which is 99, into slot 2. This writes 99 over the whole. The glowing cell is index 2. It now holds 99. Next copy, J is 3. We copy of 4, which is 5, into slot 3. The 5 moves one slot to the left. The whole has now walked to the end. Last step. The size drops to 4. Look at index 4. It still holds an old 5 in memory. We mark it gray and unused. It is now outside the size. Nothing was erased. We just stopped counting that slot. That gray cell is the whole point of delete. This is the C code for delete at an index. Like insert, it is one loop and a return. Let's read it. The header takes the array A, the current size n, and the index I we want to remove. It returns the new size. This comment is the promise before we call it. The index I must be less than n, so it points at a real element. This is the shift loop. We start J at I, the whole. We keep going while J plus 1 is less than n each time. J goes up by 1. So this time we walk the tail from the front to the back. Inside the loop we copy. We set of J to A of J plus 1. This pulls each later value one slot to the left. We go front to back so we never write over a value we still need. Then we return n minus 1. The array holds one fewer element. The old last slot is now unused. It is still in memory but no longer counted. The cost is big O of n in the worst case, because deleting near the front shifts almost everything. The extra space is big O of 1. This is a quick check. Insert copies from the back. What breaks if you delete front to back the wrong way, copying of J plus 1 from of J? Think about it, then we will see the answer. This is the answer. You would write over A of I plus 1 before you copy it, so the value at I gets smeared across the whole tail. The rule is simple. Always copy away from the whole. Back to front for insert, front to back for delete. Let's run the whole program. It uses all the array operations we built: print, get, set, insert, and delete. Let's follow the calls and see what each one prints. First we print the array. It holds 17, 42, 8, 99, 5. Next we read index 3 with get. That slot holds 99, so it prints 99. Then we call set on index 1 with the value 30. This changes index 1 from 42 to 30. We print again. Now the array is 17, 30, 8, 99, 5. Now we insert. We put 55 at index 2. The later values shift right to make room. We print again. The array grew to 17, 30, 55, 8, 99, 5. Then we delete index 0. The first value goes, and every later value shifts one slot to the left. We print once more. Now the array is 30, 55, 8, 99, 5. Last we print the size. It is 5. This is the full output. Each call prints on its own line in order. Notice it shows values and indices only, never raw memory addresses. So the output is the same every time you run it.